Hi everyone, welcome to our new video for 212 data structure. It's been a long time since our last video, so today we're learning the basic concepts of several topics. We're going through recursion, big O, and tree today. So first let's start with big O. So what big O means is that it measures the time complexity of an algorithm. So basically, it's the upper bound of how long it takes for an algorithm to run. And usually mathematically we can write it as f of n equals big O of g of n. And what it means is that there exists a positive real number, c, and a positive integer, n0, such that fn is smaller or equal to c times g of n for every n bigger or equal to no. It is kind of complicated, so let's go through two examples. So the first example, we have fn equals 3 times n, and g of n equals n squared. So based on our definition, we have 3 of n is big O of n squared. What it means is that if an algorithm takes 3n time to run, then we can say that it is under big O of n squared, which is the maximum bound that takes it to run. And the reason 3 of n, 3 times n equals big O of n squared is that if we look at the graph of those two functions, 3 times n grows linearly and n squared grows quadratically. So there's a point where these two functions intersect, and the point is n0 equals 3. What it means is that after n is bigger or equal to 3, 3 of n will be under the graph of n squared. So n squared after n equals 3 will be an upper bound for an algorithm that takes 3n time to run. And if we look at the second example, we have f of n is 3n squared plus 2n, and g of n is n squared. So we can say that an algorithm that takes 3n squared plus 2n times to run has a big O of n squared. And the reason that n squared can bound this function is that if we look at this graph of 3n squared plus 2n, we can pick a positive real number c that will make this 4n squared bound our function. So here we pick n equals 4, which means if we look at the function of 4n squared at a point n equals 2, after n equals 2, this 4n squared function will be bigger and grows faster than our function here. So what it means is that after n equals 2, we can find an upper bound for our function 3n squared plus 2n that will be always above this function. So that's basically the concept of big O. For every algorithm, we have to find an upper bound. And here are some conventions about how we wrote and determine big O. So if we have a function that takes 3n squared plus 2n time to run, first we'll only look at the highest polynomial degree, which is this part that has 3n squared, and we'll ignore the 2n part, because when we look at the function, it's this part here that determines the biggest growth. And also we'll ignore the constant. So here's 3n squared, but when we're talking about big O, we'll always ignore the 3 in the beginning. So we'll say that it will be a big O of n squared. Okay, so now let's talk about if you have a function, and by looking and reading at this function, how to determine the big O of these algorithms. So let's look at two examples. Both of the examples have two for loops. Looking at the first one, we have an int array, 1, 2, 3, 4, 5, 5 elements. And the first example we have is first, we have a for loop that loops through all 5 elements in the array, starting from the beginning to the end, and we print every element out. And the second for loop is that we start from the end of the array, and then printing out the 5 elements from the back. So the output will be 1, 2, 3, 4, 5, and 4, 5, 3, 2, 1. And if we analyze the big O of it, let's first look at the first for loop. So the first for loop will loop through each element in this array and print this out. So we know that the first loop takes n times to run. So since we have 5 elements, it takes 5 steps to run. And if we look at the second for loop, it also loops through each element in the array. It's just from backwards. So also the second loop takes n times to run. So in total, this algorithm will take n plus n equals 2n times to run, which we say is big O of n. However, let's look at another example that's also 2 for loops. So first, in this for loop, we also start from I equals 0 to I equals 4. So we loop through each element in this array. And then inside this for loop, we have a nested for loop that takes j equals 0 and then goes to j equals 1, and we print out j. So the output of this algorithm will be 0, 1, 0, 1. So print out 0, 1, 5 times. So if we analyze the big O of this function, we'll also look at the first for loop first. So we run through each element in the array one by a time. So the first loop will take n times. Since we have 5 elements, the first loop will actually take 5 steps. If we look at the second for loop, it's also looping through 0, 1, like one by a time. So it will also loop through n times. Actually, it's 2 steps since we are only going from 0 to 1. So the big O of this function will actually be n times n equals n squared, and the big O of n squared. So you might be wondering if both of this takes 2 for loops, but why this one is n plus n and that one is n times n. So the reason here is that in this function, basically our logic is that we first do this, and when we are done doing this for loop, we then goes to here. So because it's a sequential relationship between this for loop, we're having n plus n, so add them up together. However, for this one, we're not saying that, oh, after we're done with the first for loop, then we do the second one. Instead, we're saying for each element in the first for loop, we're gonna do this for loop. So basically, it's a multiplication relationship, and that's why we have to multiply the runtime of the 2 for loops together and get an overall of n squared. Okay, so next we move to a new topic, recursion. And what recursion means is that when you're writing a method in Java, it's calling itself inside the function. So if we look at an example factorial, what factorial means is that it's basically like if n factorial is n times n minus 1 times n minus 2 until 1. So if we look at this example, say inside the method factorial, we're only calling factorial. So technically speaking, this is a recursive function, but this is not working. Because if we look at example, we call factorial 3, what it does is that inside the function, it will call factorial 3 again. And then when we call this function, it will call factorial 3 again. So it will just go a infinite loop, like infinite calling the function itself. We have to have 2 conditions when we are writing recursive function. So the first one is we have to have a stopping condition. So if we look at factorial, this function, we find out that the last element is 1. So basically, when we calculate factorial, we can stop the calculation when a gets to 1. So basically, a stopping condition will be an if statement, checking if our input is smaller and equals to 1. If it does, then we just return the number itself. And then else, if n is bigger than 1, then we call the recursive stack. But when we are calling the recursive stack, what we have to do is that we have to make a progress each time. Basically, let it get 1 step closer to the stopping condition. So if we look at this line, we said if n is smaller than 1, is smaller or equal to 1, return 1, else we return n times factorial n minus 1. So n minus 1, it will decrease n by 1 each time and get n closer and closer to our stopping condition. So if we make an example saying we say factorial 3, what it does is that first check if 3 is smaller or equal to 1. It's not, so it gets to this else step. We'll return 3 times factorial 2. And when we're calling factorial 2, it will have another call function on the call stack like here. and we're inside this factorial 2 call right now. And we're checking if 2 is smaller or equal to 1. It's not, so we get into this else statement saying we're returning 2 times factorial 1, so we're calling the function again, and we get another function onto our call stack. And inside this factorial 1, we're checking if n is smaller or equal to 1. So right now, our n equals 1, so it will stop, keep calling factorial again. It will return n, so it will pop this call on our call stack and returns 1. So basically here, this function call gives us a value 1. And right now we're inside this function call. And this function call saying we're returning 2 times 1. So we'll pop out this function and returns 2. And right now we're back into our factorial 3 function call. And here it said we're going to return 3 times 2. So it will pop out this function call and returns 3 times 2, which is 6. So basically, it's how a recursive function works. We have to identify a stopping condition, which is an if statement. But this is not unique. You can have a lot of stopping condition that does the same thing. So for example, here I use n smaller or equal to 1. But you can also use if n is smaller than 2, or if n is equal 1. So as long as you identify a stopping condition yourself that works, it doesn't really matter like what exactly you use. And also in the else statement, if the n is bigger than the stopping conditions you have to return something that will decrement the input by 1. That's like getting closer to your stopping condition. So as a programmer, when you're coding the recursive function, please don't get into a logic black hole here. Don't like keep thinking that, oh, how is this part gonna give me the final results? Because sometimes here, our input is really small, so you can actually write down the call stack pretty easily. But sometimes the n get really big, you'll get yourself into an infinite like logic hole that you'll never get out. You'll get yourself really confused. So when you're writing recursive function, you just assume that this next function call will give you the correct answer. Just trust it. Just assume that the previous function call will give you the right answer, and you can just use that answer directly and then return the final answer you want. Now let's go to a new topic about tree. So basically, tree consists of several nodes and a lot of edges between this node. It will be a root node, which is the highest node basically in our tree structure, and the root can have a lot of children. But in this course, we're mainly focused on binary tree. What it means is that each node will only have a maximum of 2 children. So if we look at this example, the root node has 2 children, and the left child has 2 children itself, and the right child has 1 child. And we also call this 3 like very bottom child as leaf nodes. So leaf nodes doesn't have any children, and root nodes doesn't have any parent, like anything above it. And for those 2 in the middle, we call them branch. So when we define a tree, you can define it as null, which is nothing, and you can also define it as a data structure that consists of a data, a left, and a right. So note that the data here can be any type, like it can be an integer, it can be a double, it can be a string, and other things. But the left and right here, this should be a tree structure. So if we look at several examples, so here, this is a tree of 14 null and null. This is a tree that has integer data and 2 children. This is null. And if we look at this, 14 null and 6, it is not a tree. Because here, the 6, it should be a tree type. But the 6 here is an integer, so it's not a tree. But if we want to create something that has a 14 as a root and a 6 as a right child, we have to define this in a tree structure, like 14 null and 6 null and null. So this was the tree. And another concept is about height and depth of a tree. So if we draw a tree like this first level, we call it level 0, and then we go down one level, this is level 1, and then go down another one, this is level 2. So if we're talking about the height or the depth of this tree, it will be 3. So in the lab, you're given a binary tree class that has a bunch of functions like get data, get left, get right, and like set left, set right, those things. So we're going to talk about how programming works. So if we're going to initialize a tree, it's basically the same as initialize other data structures. You have to declare the type of it, which is binary tree. And you have to tell them the type of data, for example, double. So this double means what is the type of my data here. So if I say this is a double, and then I name it like T1. So after you declare this, you have to initialize the tree. It's basically saying new binary tree. So for example, if we give it a data of 1.5 and null. So right now we're creating a tree called T1, which has data 1.5 and no children. So T1 is only referring to this node right here. And if we want to create a child under this node, we can use the set left or the set right method, depending on which direction you want to go to. So for example, we want to give T1 a right child that has the data of 3. We'll say T1.setRight. And inside this input, we'll give this node right here. However, we just said that the left and right should be tree instead of just a number. So if you just say set right 3, it is wrong. So we have to define this node right here as a tree structure. So we can say set right and create another tree. This new tree will have the data of 3, and then it doesn't have any children. So inside this new initialization, we'll create a new node with data 3, and then we say T1.setRight. This node will create this hierarchy over here. So after we add one more node into this tree structure, note that this notation, this variable T1, still refers to this node itself. It doesn't refer to the whole tree. So how do we represent this node right here? We cannot say T1 because T1 is only here. So we have to use the getRight method we have. Since this tree with 3 is the right child of T1, we can use T1.getRight. So getRight method will return us a tree structure which represents this node. However, getRight returns us a tree. So if you, in the lab, you may encounter that if you say system.out.print, for example, you say .print T1.getRight, you will expect it to print out 3, however, it doesn't. It prints out some weird representation which represents the memory address of this tree structure in the computer. So if you want to print out 3, you have to actually print out the data inside this tree. So instead of just say T1.getRight, you also have to call getData, and getData will actually return you a double. So for example, it will return you 3.0, and this will give you the data of the tree.